need. Hey, yeah, so I'm Ben. I'm going to talk to you about Turn a Big Iron, which is a bit tongue-in-cheek, to be honest. But yeah, so this talk is a little bit, it's about big data technology, really. It's probably a bit different to the other talks of the day. I work in the enterprise space, so it's more around the technologies, how they kind of grew up, and how we've used them for a slightly different use case. So you probably remember when that was like the database world, or at least that was the majority of it, the bit that most of us looked at. There was an oligopoly of basically 4, and it was all pretty easy, which was nice. You just kind of picked one. These days, it's downright confusing. I mean, there's been a number of them mentioned today. You kind of need a map, and even with this map, how many times has this map been up today?
No, first.
First time, really? Okay, well there is a map of the database landscape. It's huge. I mean, I work in this field and I don't know all of them. But anyway, look that up online, it's quite interesting. The categorization is pretty good. So anyway, the point is that there's lots and lots of it. And it's actually really exciting. Well, I find it very exciting. Things have somewhat stagnated to a certain extent, and you've got this kind of new influx of technologies and ways of thinking about how we store data. And it's kind of got, and it is very interesting. There's quite a good paper by a guy called Joe Hellerstein. Anyone know who Joe Hellerstein is? Ooh, we got a few. Good. He's probably one of the top database academics, and he wrote this paper back in 2001. He's very much from the sort of database background. And bearing in mind, obviously 2001 was quite a long time ago, it was before a lot of this stuff happened. And he said, databases are commoditized and cornered to slow-moving, evolving, structure-intensive applications that require schema evolution. The internet companies are lost, and we will remain in the doldrums of the enterprise space, that would be me, and maybe you, as databases are black boxes which require a lot of coaxing to get maximum performance. And this was quite insightful, really, considering the time. So what happened? Well, obviously the internet happened, the web happened, and the number of users, there being a lot of users and people needing something that could actually scale to millions of requests, concurrent requests, which obviously couldn't be serviced by your traditional database. So we kind of changed scale, and probably more importantly, we changed tack. We changed the direction, or at least the technologies that were used now take a slightly different direction. So you start to see technologies which favour simplicity, pragmatism, attempting to solve an insoluble problem. So a lot of this really came out of one of the key companies was obviously Google, who were obviously trying to index the web, amongst other things, and deal with the amount of data that's generated by a very large corpus of people interacting over the internet. And what's also quite interesting is that the technologies were really unencumbered by tradition, and this has been a great point of contention with the database community, with some quite vocal members who were maybe not that impressed with some of the well, actually things like Hadoop, which they see as being naive, when, or at least maybe not taking into consideration a lot of the academic thought that's happened over the last 40 years. But I think I see that as being good and bad. So you've got a nice fresh look at a technology problem in a slightly different context. So this came with this different focus. So traditionally, you've got global consistency. We're moving to local consistency in the NoSQL world. Schemas are no longer so important, so most technologies are schemaless, based around the idea of an unreliable network, because obviously if you're scaling to many machines, you need to consider that. You can't guarantee that your network is going to behave the way you want it to. And similar to the schemaless thing to a certain extent, but the support for unstructured data, or possibly semi-structured data. So the relational camp's been pretty busy too. So you've got that whole NoSQL stuff, the big data technologies, the Hadoops, and that map of different things popping out of the NoSQL world. The relational camp, I think there's this realization that the architecture was insufficient. There's another quite good paper, not quite a bit later by probably the other really big, or one of the other really big database academics, Michael Stonebreaker. And this is actually, it was actually to do with Vertica, isn't he? Vertica is one of his babies, but this quote was in relation to VaultDB, which is an open source one. But he says, because RDBMSs can be beaten by more than an order of magnitude on the standard OLTP benchmark, there is no market in which they are competitive. As such, they should be considered a legacy technology more than a quarter of a century of age, for which a complete redesign and re-architecting is the next appropriate step. Slightly controversial statement, but he does have a point. He intends to do that, by the way. Both have a point and also maybe overplay it slightly. But his real point was the fact that no longer can you have this one-size-fits-all solution to data storage. I mean, he's who's looking at more from the OLTP, the sort of fast data viewpoint. So on the relational side, there's been quite a new impressive breed, a bunch of products. So the last speaker had a few of them. Was it previous speaker to that had a few of them up there, but a lot of them sort of 5 to 7 years old. Designed slightly differently in the context of the technology space we have today, so particularly around things like clever use of SSDs, 10 gig E. Most of them are shared nothing architectures, sometimes avoiding things like indexing strategies explicitly. Dropping some of the traditional tenets you'd associate with a traditional relational database like reference and integrity, and often very fast, right? So a lot of these new technologies are incredibly quick. But I think the important point from my perspective is that both of these types of solution, both the SQL and the relational, I should say, and the non-relational solutions have clear value. Oh, that didn't really work, did it? But the key point really is that it's not a question of size. In fact, this has come up a lot today. But whether or not you are if you're in the petabyte range, which I would imagine the majority of us are, certainly in the enterprise space, then whichever size is not the gating factor. Most of us are going to be in this majority region. What you really need to be interested in, of course, is more kind of utility. And that's what tends to lead us to this idea of composite offerings, this idea that we need different solutions to do different things. Again, that didn't render very well. So this is one typical pattern. There are a number of different ways that you can sew together a number of solutions, but you can have some kind of big data store, as it were, which is doing unstructured data, possibly MapReduce and key value on that side, and then that being imported into some data warehouse, some kind of tuple store with maybe an in-memory OLTP engine on the other end. But really, the key point here is that the architecture is disconnected. So what does that mean for the enterprise? Well, I'll apologise for the fact that I've got a better number for this, but this reference I've been using for a while, and it goes back to 2009, so it is obviously out of date. But most enterprise databases, they're not that big. They're certainly around a terabyte even today. I know this mainly due to the fact that most database technologies that we use can't scale much beyond that without some difficulty. And certainly in the company I work in, that still remains approximately true. So my point here really is just that the enterprise databases themselves are not that large, but of course we have a large number of them. And obviously the data content as a whole is pretty large, but it's distributed around a large number of systems with obviously a very large number of different data models. So we have strategies for getting all that data back together. Store and forward is probably one of the most popular. The use of messaging systems to sew data, or at least to pass data between different systems, allow them to communicate. For a bit more organised, we'll have something like an enterprise service bus, which will structure it somewhat, maybe with the addition of an enterprise schema. I'm not going to debate whether or not I think that's a good idea. But the key point is that most of our data is private, right? Most of our data is not accessible, and the bits that we do tend to expose tends to be an afterthought. It's something that is in a schema which is designed for transport. Services are a really good way to solve this, or at least to aid communication between these different databases. That pattern works very well, probably the most successful pattern to date. But as the data load gets bigger and heavier, it gets much harder much harder to work with, particularly when the data is heavy and there's a need to kind of join different relations together. If you've got a bunch of services, it's going to work for fairly lightweight requests. If you're starting to do things like trying to join disparate data sources, even with virtualization technologies, it tends to be quite difficult. So what this does is it tends to lead you down to the line of the enterprise data warehouse. Who works in a company that has an enterprise data warehouse? Ooh, no one. That's probably a good thing actually, because they have to a certain extent fallen out of fashion. I noticed Gartner had them on the out list recently. So this is obviously this concept. Many of the vendors will promote this idea. Whether or not you go down the enterprise data warehouse route or the virtualization route, you're either bringing all your data into one place so you can query it, or you're doing something that's more kind of a federated query. And this is an old pattern. It's well researched, and it can work. In some companies it works really well. In other companies it doesn't work so well. But the idea is obviously get all your data into one place, put it in normally a big database, and run your reporting via some ETL layer. And we're back to this picture again, which didn't quite render. So big data technologies can sometimes, or the NoSQL technologies can sometimes be used as a mechanism for aiding your ETL, allowing you to look at different types of data. You might be using whatever it is you might be mining in order to get it into your data warehouse. But the general pattern would be some kind of ETL there, reading from message bus. Okay, so this is another quote from VLDB last year, one of the keynotes Dave Campbell from Microsoft, where he just said the ability to model data is much more of a gating factor than raw size. And what this really means is that if you're in that distributed world where you've got a large number of different databases and you've got all those different data models, this is true actually with any, this as it scales really with the complexity or the number of data sources that you need to integrate, actually understanding what the different data models are is the biggest gating factor. That's just a really hard problem. No piece of technology is going to magically solve this problem for you. It's just grunt work. It's just hard if you actually want to do that. And it's slow. And yeah, I said there's not that much you can really do about it. All you can really do is try and be a bit smarter about the way that you go about doing it. So, well, our approach to this, where I work, so we do something that's slightly different to some of those other architectures. It's a pattern which is being used in the past in different ways, but we use this idea of a late-bound schema to try and get around some of the limitations of bringing data together with a static schema. So the idea is that you when you're integrating data, rather than going through the approach of saying, I'm just going to have one big enterprise schema, and we're going to import all our data in according to that schema, instead you import the data in a more of a raw form. So you don't worry too much about the schema when the data comes in. You are agnostic, effectively, at that point. And instead, the schema is late bound. That's to say the schema is a projection that sits on top of the raw data across the grid. So that kind of combines both the structured and the unstructured approach, but to sort of give the same end. So in our case, it's a grid of machines. It's got its late bound schema. All the data is sharded and immutable. It's geared around sort of low latency and high throughput, sort of grid-based use cases. Working in a bank, so most of a large proportion of our data access is from a grid. All data needs to be observable, that's to say that you can listen to it. But most importantly, it has these two standard interfaces. You're either going to go through the standardized enterprise schema, or alternatively, you can just view the data in its raw form, which is going to use at your own risk. So what does that look like? In some ways, it kind of looks similar to the previous patterns. The main difference is that the two are literally layered one above the other. So if you want to, you can either come in and see the underlying data model, or you can see the standardized data model, either in a sort of relational and in our case an object form. That's really very much your choice. And then there's an analytics piece that sits off to the side. So what this does is this helps you to loosen the grip of a single schema. It helps you to solve some of that problems. That problem of how am I going to get all of those different data sources to integrate into one place at the same time without it taking ages. It allows you to do it iteratively because you're bringing the data in with its natural data model, storing it with that natural data model, and then iteratively standardizing it. So you can see in this example we have a bunch of different data models, and then the standardized model effectively can grow over time. That being, in my experience, a more efficient pattern for dealing with this problem. There are, of course, other ways that you can do this, but this is the one that we've been exploring. So what we have is a slightly different way to layer the technologies available today to solve what might be considered a more traditional or familiar problem. And then, on top of that, if you can do that, you can then obviously start to add some kind of standardized processing. So in our case, we do risk calculation processing which is shared across the bank. So risk calculation is actually federated, so it uses the federated data model on something like position keeping, which is a fairly generic task. At least at its core, can be done against a standardized model. And at that point, I guess I leave with the question if maybe we have gone back to the world of UNIVACs and mainframes. But I'll leave that up to you. That's all I have to say. Thanks very much for listening.